Can everybody hear me? Yes?
Yes.
Thank you. All right. All right, so what I would like to do is to suggest that for you to better be able to learn the material specifically as it comes to the Smith chart, I suggest, and I need also to put the video because I suggest that you watch you don't only look at the material, but you also watch the video from the lectures. Because on the Smith chart, when you place things, I describe the circles as opposed to just seeing what it is on the document, in the document. So the video is important. Now I have put the video for a section, there's your section on Wednesdays. So you see, I will do that for the other section too. Both videos are, for both sections, are also on the home screen. Let me see. The Monday, okay, I need to put the Wednesday. Usually it takes me time because I have to edit them a little bit. I have to remove any personal information. So I have to go screen it once and edit it before I put the video. But in any case, I will have today, by the end of day, I will have all of the videos from Wednesday. You have yours. I will put a video for the other class for the afternoon, but also the videos from today. And specifically the videos you can argue not necessarily need, especially if you have been in class, but you definitely need them even for those who were in the lectures because they help you remember how we find things on the Smith chart. So today we are going to continue with this problem, but what I would like is to remind you where we started. So we wanted to design a network, as we call it. So the name, the official name for whatever we're going to be the antenna and our source is a matching network. That's how people communicate, all right? So if you say, I'm designing a matching network between an antenna and a source, everybody knows what you're doing. So, and then we give here the source characteristics, all right? Frequency, amplitude, internal impedance for the source, real. And then also the antenna characteristics, which is just the input impedance to the antenna, Z-sub-A. And from there, we followed the process. I asked you 3 questions because I'm gonna always do that in this class because it is important to help you, somehow channel your thoughts on how to go about it, all right? Because design problems are a little bit chaotic, okay? So the design space is not just one point where you go to find it. There are multiple solutions. And we are not ready yet to say what is the best solution. I cannot expect you when I give you this problem and say, design the matching network for you to come with the best solution. No way, all right? It takes years to be able to learn that on your own. So I'm gonna guide you in solutions with some questions like that. So in the final, for example, and I will not give you all of this, but I will tell you a problem like that, and then I will give you guidance on how to go about your design. The first design here is only one transmission line. So I'm asking you a question, can you use only one transmission line section, all right? And what we said for this is because this Z-sub-A has a real and imaginary component, we cannot use a quarter wavelength transformer. The only network we have seen, all right, the only distributed network that has only one matching network, that has only one section of a transmission line is the quarter wavelength transformer. Remember that, okay? Very important matching component. We use it extensively everywhere. However, only at the point where you have achieved a real load or a real impedance at the end of this. We don't have that here. Therefore, we say no to this. Okay. So we go to the next group where, in addition to a transmission line, we're going to use something else. So there are two possibilities. One is a transmission line, which is a distributed element plus a lamp. And that approach is called the hybrid approach. So let me also write here to remember the terminology that I'm using. So a transmission line, I will write it on the side, transmission line or any combination of transmission lines is a distributed element. Why do we call it like this? We call it like this because in addition, everything else that we've learned before the transmission lines, we call them lumped elements. Transmission line is called distributed because it has a physical dimension, all right? It has a physical dimension, you see it. As opposed to what? Lumped elements, where lumped elements here circuit elements, obviously, all right, are a resistor, an inductor, and a capacitor. Because they do not have the way we use them, they are so tiny that theoretically and practically, we assume that they have no dimension. Even if, as you go to very, very high frequencies for operation, everything has a dimension, all right? Because we print things, we make things. Everything that we make has a dimension. But now, our operating frequencies are at that frequency range, and for everything that we do, as a matter of fact, for an iPhone, for everything that we do, unless you go to telescopes that have terahertz frequencies, everything that is an R, L, and C, whether you put it there or you print it, is considered to be so tiny that practically we don't worry about size. And they're called lumped elements, all right? Now, a design that has both distributed and lumped elements. So in fact, if I want to be correct here, I will remove that and do this here so you remember. And the transmission line is a distributed. A design that has both a distributed and a lumped element is called a hybrid design. And therefore, the circuit that you will make out of a design like that is going to be called a hybrid circuit, okay? And so this is hybrid. And a design that has only distributed elements is called monolithic, all right? So you remember, I don't care that very much. I'm not going to test you on this, but you know, when you start reading stuff, this is how people are referring to those designs. This is a monolithic. Do you remember the word monolithic? From the monolith that was in the 2001 movie. It means, it's a Greek word. It means made out of one thing, one type, one material. Now it's not one material, there are multiple materials, but one type. So this is monolithic design, monolithic circuits. When you hear integrated monolithic circuits, all right? It's this, all distributed. When you hear hybrid designs, they include both distributed and lumped. All right, so that's the terminology. Anyway, so then I told you how to put together what you know and to outline what you do not know. It's very important because there are so many parameters here that you don't want to forget. And then we went through this. I'm not going to go through this again. I'm going to stop here and then remind you what we did. We said the first thing when we want to design, we did the impact parentheses. We did the hybrid design that involved a transmission line and a lumped element by using a capacitor and a quarter wavelength transformer. All right, it is in the notes that we did last time. Here is how we do monolithic designs, everything distributed, Smith chart. So first thing we do is to then remember that the Smith chart is a space where we map impedances. Every point of the Smith chart inside the inner ring, right? Every point represents an impedance. Now, we keep it there even if we will see in our some of our examples next week. Then you can go, and today I guess I'll show you, you can go from an impedance to an admittance. But what you see here, what you read here, when you start are impedances, okay? So we try to find out, then you go on your line, and then you place on this line, you do that from the beginning, you place the input port, the output port. You know, your output port is where your load is, all right? If you remember the original design. The original setting. Your output port is where your antenna is. And you want to use a section of a line and something else in addition to just a section of a line. So that here, from the matching condition at LA prime, your input impedance becomes equal to R sub S. Remember that from the matching condition. So we talked about this last time. And therefore, you need to think, how is that translating on the Smith chart? Where is my load and where I want to go? So always on the Smith chart, the place you want to go is the center of the Smith chart. Always. The center of the Smith chart shows where your load has become equal to the characteristic impedance of the line. All right, and that's your matching point. That is it. Because if at any point on the line you match, if at any point on this line you manage along this direct, at any point here, you manage to make your input impedance at that point, you manage to make that, whatever point that is, equal to Z0, then practically at that point on the line, you have achieved a perfect match. Your reflection coefficient right there is going to be 0, which means that any other point before, after that, is going to also be matched. You can put a kilometer of a line here. And I'm exaggerating, obviously. You can put as much line as you want after that, and it's still going to be matched. Obviously, you're not going to put extra line unless it's determined by your architecture in the circuit. We try to be as small as possible. Remember that? So small is good because you want to have small size and less losses in the system. So you try to have your lines as short as possible. So you can make them, obviously, because sometimes if you tell me that this line, when I make it, it's going to be like a microstrip. When you tell me that the width, you remember how the microstrip is? The microstrip is like that on a dielectric, all right? All right, it's a line, it goes like that. And let's assume that that's how you're going to make it out of a microstrip. If you tell me that this width of the microstrip, the width of it is like 10 microns with a given, with silicon, for example, substrate. so that, or silicon oxide substrate, so that the Z naught of this line is 50 ohms. If that were to be 10 microns, and then you find a length which is 1 nanometer, it's not going to work, all right? Or even if you find a length that is 10 microns, it's going to look like a little square. So you have to add something to make it reasonable. In fact, the minimum length is whatever the distance is between your load, the physical distance on your circuit between your load and the source. And usually those are determined. But in any case, so you practically, after you achieve that matching, then you can add whatever line is necessary out of the architecture. Okay. Now, we know before we normalize all of the impedance. We said that. We found the impedance by looking at the real part from the red. So the normalized impedance was 2 plus 8, 0.6, 0.6. And 2 from the red circle and 0.6 from the green one. The intersection of the two gives us the impedance at B prime. That's the output point. I'm gonna go to CC prime and I want my CC prime, which is exactly where I connect to my source, or any place, you know, before that. I wanna go at the center of the spectrum. How am I gonna go there? I cannot go straight. I cannot go from B prime to CC prime. There is nothing, there is no path. You don't see a line to connect there, okay? So what do? I can only move in 3 directions. If I move on the constant VSWR circle, that implies that I'm moving along the transmission line, all right? You remember we said that. Therefore, if I start moving on the transmission line without adding something, if I start moving on the transmission line, then how that shows on the Smith chart, it shows by the constant VSWR. Another way, if I move along a red circle, that implies that whatever I do, that I'm doing something. I don't move anymore on the transmission line. It shows like I'm moving on a circle, but ideally, any movement along this circle, it implies that I'm introducing a reactive element. Why? Because all of the elements, all of the impedances of this circle have the same resistive part. So if I go from BB prime to this point, what it means is that I'm adding something at BB prime that moves my point from the changes, and what I'm adding is reactive, that changes my reactance from 0.6 to minus 0.6. That's what it's on. To change my reactance of the load from 0.6 to minus 0.6, I'm adding a reactive element, all right? So moving along the red, it shows that I'm adding a reactive element. Moving along the green circle, it's a circle, but we don't see the whole circle. Moving along this green dotted line here, it implies that I add something so my reactive component remains the same, but my resistive component changes, which means that I add something, I add a resistor, all right? So moving along these lines, like the red, these circles, is like I'm adding a reactive element. Moving along this green dotted, it means like I'm adding a resistor. Of course, in a matching network, you will never add a resistor. Why? Because you are going to lose power. You add a resistor somewhere, part of your current is going to flow through the resistor, and you lose it. Okay? So the only thing that is acceptable is to add a lumped element. But so we're not going to move here since we don't do a hybrid design. So the only thing I can do by excluding the other ways of transportation on the Smith chart is to move around this, number one. So I move around. Okay, so I go here, but then I can go around, right? Every time I go around by half a wavelength, what did I say is happening? Find the same impedances, right? So your impedance, if I move on my transmission line, okay, so here, if I move on my transmission line by a distance here, all right, by this distance, which happens to be, and I come say to point B, C, this point. These are so close to each other that I only have one other point corresponding to this point. So D, if I come say to point B, and practically the distance between D and B is like half a wavelength. Whatever I see here, I will see here in terms of impedance, all right? The impedances on a transmission line repeat themselves every half a wavelength. Okay, so that's what the Smith chart is telling me. Therefore, definitely I have to move less than half a wavelength. I'm not gonna go around. I have to move the shortest possible distance because we try to minimize distances in a practical way. I will move to the shortest possible distance that can eventually get me here. Okay. So if I move here, then you can get me to this point. And then from here, the only way to move is by following this circle that goes through the center of the Smith chart. Now, you remember what we said about these circles? When I move along a circle, practically I add a reactive element, but I cannot have a hybrid design. So the only way I can add a reactive element is by adding a stub. All right, what is a stub? A stub is a section of a line. Yes.
Along the constant DSWR circle, that's dictated by where we're starting on the line, right? So if we're starting at BB and we want to go to AA, then we have to move towards the generator along that line.
Yes, always, because here is your load.
Right.
And then if you move, the only direction goes towards the generator.
So it is dictated by where you're at on the line.
Exactly.
It says which way you go around.
Always. If you are on any place on the line and you go towards your source, you go clockwise. But if you are at any point on the line and you move towards your load, you go counterclockwise. All right, but in our problems here, for simplicity, we'll always move clockwise to do that. Now, you could say the following to me. Say, you told us that I will not go and move around this red circle because it's like I have to add a reactive element. And then I do it if I were to add to move around this red. First of all, it takes me away from CC prime. The second thing is that even if, let's assume that I was somewhere here, my load, and I could move along the circle, it's very difficult to place anything at your load because it's a port there, all right? You never place things anywhere at your source, at the input port or at the output port. Whenever you match a network, you never place anything right at the port. You may do it on paper only, but practically you cannot do this, all right? Because at the port, you have other issues. At the port, you need to connect whatever matching circuit you have to your antenna. And then you should not worry about adding a stub there or adding a capacitor or doing something. You may do it on paper and it's gonna be an acceptable theoretical solution. But practically, you're not gonna be able to make it, all right? Because people worry about other things. So for example, my antenna may have a coaxial input. And then I need a coaxial output out of this. So I'm not, where am I gonna put on the coaxial output? Or the that point stuff. I can't do it, all right? So obviously you need to be somewhere inside and away from the ports, remember that. Practically, you don't put anything, either at the input port or the output port. However, theoretically, it's not wrong, but practically is. All right, so now we are here and we want to move from E prime, all right, which, where is it in my notes? Let me see where I put E prime. Okay, I'll put it here for a second. Okay. I am right here. What I did before is to introduce the concept. This is a parenthesis rather. So let me show it as a parenthesis. Just to remind you what is a series stub, which is open. So let me see. I'll do that here. So you remember this is a parenthesis and ends here. So you remember that you can have a series stub or a parallel stub. These are the options. You can have an open or short here, an open circuit, or to write it here, or, oops, not, got that, or short, short circuit, and the same thing here, short or open at the end. All right, you have 4 possibilities, and usually what is going to tell you which one of them is the most accurate is your architecture. All right, theoretically, you have 4 possibilities when you add a stub: series or short, series or shunt or parallel, open or short. But practically, you're going to only use one. So we go from BB prime here to EE prime. So we are here. So what I'm saying is that I found myself at EE prime from BB prime by moving by a distance D on the constant VSWR circle. See, I put the distance D, but I did not tell you how to find it from the Smith chart. So the first thing we're gonna do is to find this distance, how we find the distance. Okay, so here I'm going to draw, use a different color so you can differentiate it. I'm gonna draw 2 lines. One line is gonna go from here. It's gonna be from the center of the Smith chart through my starting point. I started at BB prime. And the other is gonna be from the center of the Smith chart so through my endpoint where I stopped. And that's EE prime. So what I remember is that I started here and I ended up here as I was moving. Now, why do I do this? Because the only way to measure length as we move is to go to the outer circle. Remember that? So what I have to do is to go to the outer circle, and then what I will do here is to highlight it. Highlight the circle I'm going to pay attention to what it says. That on the Smith chart represents the physical length. So it starts at point, it starts at point 2, 2. Let me write it also here. Point 2, 2, 2. That's why you get very good readings, because see how many digits I can get from the Smith chart. I can get 3 digits, all right, which is very interesting. And then I'm terminating, look at the number here, it's 0.34, 0.35 there, so it's 0.3. It's therefore, and I'm ending at 0.345 lambda, always in lambda. Okay, if I started at since I started at point 0.222 lambda, and I ended up at 0.345 lambda, how much is the length that I was able to cover? The difference between the two. All right, so the length of the line, so that I was here at BB prime, and here I am at EE prime. Therefore, the distance between the two places, which is here, this D distance is going to be 0.345, wasn't it? Okay, thank you. 45 minus 0.222 lambda, which in fact is going to give me 3, 2, 1. Gonna give me a D, which is equal to 0.123 lambda. So I found exactly the place where I'm gonna start. Okay, with this one. Did I? Okay, now the other thing that I wanna do next is to find how much impedance I'm reading at this point. So far, I'm very close to where I wanna be. I still have a distance to go because my CEE prime has an impedance, all right, my CEE prime impedance. My ZE prime impedance here, I see how much it is from the Smith chart. How am I reading it? Okay, let me also correct this one for a moment. E prime. So the impedance here that I see on the Smith chart, which is here at ZEE prime, that impedance I can read how much it is. I know that I am on this circle because I stopped. That gives me normalized real part 1. So I know, and I will, that is 1, as you can see here. And then I write the circle that is going to give me the reactive part. And that circle intersects the inner loop of the Smith chart below in the lower half space, and therefore it's negative, and then has a value of 0.9. So it gives me a value of negative 0.85. So what I was able to accomplish by coming here is to just make, let me also move this a little further down. I was able to do an important thing. I was able to turn the real part of my load to 50 ohms. So this one here is 50 ohms. So now I'm left with the reactive part. I need to take care of it. If I can cancel the reactive part, which is capacity, then I would be left with 50 ohms, which is what I want to have. Yes. Yes, but we don't want to do hybrid designs. So here we are doing a monolithic design. Everything is distributed, all right? So I have to find something else since I cannot use an inductor, as you said, which was correct, but I cannot use it. That's what they told me. And I need to find something else that can give me the equivalent of an inductor. So what section, from what we learned in the past, what type of a transmission line kind of a circuit is giving us a reactive input? Which one? Oh, a parallel, yes. I mean, parallel is how you connect it. All right, here we can connect it like this, or we can connect it in series. We'll go to that one. But do you remember from what transmission lines with loads that we did at the end? What kind of a load in a section of a transmission line gave us in the input reactive only? Open or short? Remember that. When a transmission line is terminated in an open or a short, it gives a reactive load. And here is, I'm gonna make a parenthesis and then I will put the stubs down here. It's very hot. Sorry, in my office, the temperature is 65 degrees. So I have to take an extra coat when I go there to work because the system is broken. So I'm overdressed all the time. Okay, so the here, let me get these two. All right, so this is a place where I can write things. Here, let me add a page. All right, perfect. All right, now I'll write something that we have seen before, and I will just remind you. If I have, so let's assume that I want to put here open-ended. Or open-circuited, all right, transmission line. That is called an open circuit stub. That's the name we give it. Okay, how does it look? It's transmission line like this. All right, it has a characteristic impedance. We can use it, Z not 50 ohms. It's up to us since we are designing. And usually 50 ohms is a standard. Here is open circuit. So I will put it like that, which means open. All right, but you see that it's terminated. It's not just undefined. So let me put the ports. Input port here, A prime. Output port here, B prime. And therefore the input is here. Since it's open-ended, it's one port. All right, so I want to find how much is the input impedance, assuming that this is L. So I'm going to find Z input here at A prime. All right, what is the formula for Z input on any transmission line? The Z input at any point, if you remember, Z is practically, let me see what time is it, okay? Is practically Z naught ZL plus J Z naught tangent of beta L over Z naught plus J ZL tangent of beta L. All right, how much is your ZL? In this one is open circuit, infinite. If it's infinite, this practically can be ignored, all right, because it's so small compared to ZL. And this one can be ignored. And therefore, what you have is the Z input at a point L, here Z equals L, of a point of an open circuit stub, so of open circuit stub is equal to minus J Z naught tangent, in fact, one cotangent, sorry, of beta L. Okay. Now, if the stub is short circuited, you can do the same thing and for the Z input, I'm not gonna rederive it. You can follow the same thing, the Z input at L of a short-circuited stub, short-circuited stub is equal to J Z naught tangent of beta L. All right. So what does that tell me? Now from that, I need to remember, and we have seen that, but now we put it in context. All right. So for a short-circuited stub, let me write it here, move that. So you have it in your notes here. Short-circuited stub. So it's this one. Okay, not. Okay, and the open is here. All right. Okay. What does that say? That a short-circuited stub will be something equivalent to a capacitor. Okay. See that? That could be a J omega, excuse me, inductor. That could be the J omega L. So it's equivalent to an inductor. Equivalent. Assuming, of course, that the value of tangent beta L is positive. All right. Equivalent to inductor. And then here in parentheses, I put tangent beta L larger than 0. Remember that. And then this is equivalent to a capacitor. To capacitor. All right, assuming again that cotangent beta L positive. All right. So now this is important to remember. Okay. And here I will move this one down here. So now that I have found myself here, I know what I can add here. I can add a short-circuited stub that's going to give me the equivalent of an inductance. All right. So here, I do all of these steps so you can see it. So I identified exactly what I said. All of this is like a schematic representation of all of the discussion we had, right? So we are here. So here we identify that we can put a short-circuited stub that is at this point is going to create an inductance which is going to cancel that. All right, and that is somewhere in the line. All right, remember we are at E prime. Okay, so now to be able to define this stub, since I assume the Z naught 50 ohms, here I have assumed that this is Z naught and this is Z naught, and I have assumed the Z naught is 50 ohms is a standard. The only thing, what do I have to identify in this stub to make it cancel this? It's length. Okay, so I have to find this one. And I would call it this abyss as the length. So this is the only thing that I do not know. All right. How am I going to find it? Very simple. And this is an open circuit and this is a short circuit. All right. You need to remember that. If I need, since I'm going to always move, short circuit for the stub is the load. Remember that? So as I move up to its input port, I move towards the generator. I'm at the end of the short stub, and anyway, I have to go towards the generator. Right? So I will start in a short circuit, which is 0, and I will move around here until I find this point. And that's the shortest distance. And if I read it here, out here, that's 0.383 8. For a short-circuited stub, this is the length. All right? This is for a short-circuited. Excuse me. I will replace my notes with this one today, since we have added some new things. So that is the distance of the stub. All right. Now I will stop it here because I think it is, no, we have 5 minutes. Okay. Somebody, I'll make a parenthesis here. Somebody can come and say, well, if I use a short-circuited stub, then look how long the length is, right, of the stub. It's too long. For some applications, if your stub is longer than your line, then you have a problem, all right, because it's going to look really weird. As a matter of fact, if I were to do this here, it could look like this. Assume that is a microstrip. So for example, let me also add here page. So let's assume I try to make that. So it's I'm using microstrip, substrate, the microstrip here, and here is the ground. All right. And let's assume that the microstrip looks like this. And here is the end of the substrate, like that. And then somewhere here is the opening to my antenna. You can assume that the antenna can be a dipole, or can be a patch antenna. I don't know, you have not seen them, but this is, I will show it to you so you can relate to some real circuits. Okay, so a patch antenna can look like this, like a square patch. All right, and it is on the same substrate with your microstrip line. And practically, so your source, let's assume something also else. Let's assume that this is a little longer. Your source is somewhere here. Your source could be, for example, the end of your transceiver. All right, and this is the substrate on which the line is, and this is the ground. I'll do a better picture for you. All right, and let's assume that you have this much space to match this one to that. All right, and assume that you have already found the place where you're going to add something, and somewhere here. Let's assume that this is your distance D, original distance, all right, where you're going to add something. You found that. So now I found a small distance for that. I found 0.1 something, right? Remember? Now I need to add a stub. The stub is going to be in series, even if, you know, it's for microstrip, it's difficult to a series stub. It needs to be in parallel. But in any case, what I wanted to tell you, even if it's not, let's assume you wanted to add a stub. Here, the stub that I'm going to add is going to be parallel because it has the same ground. All right, the transmission line. But if I were to add it here, it had the same length. It would look like this. And then it would not be something that it would almost look as long as your antenna. It could look like this. So very close to your antenna, that's a parallel stub. I will put a better picture. Very close to your antenna, you have a stub that looks like this. You know what's going to happen with the stub? It's going to start radiating because it's as long as the antenna. It's going to interfere. A lot of times people will bend it, but they don't want to hit something this long. You always try to keep your stubs to be short. So on the basis of that, in your design, you say, well, that's too long And I can see on my chart that I can have an open circuited stub, all right, which can be a lot shorter. Now, this open circuited stub, the way it is, if it's open circuit here and I move down here, it gives me here's something that I needed a positive. Why did I stop there? Okay. Let me go back. I may have. Okay, so I'm here and I want to move that. The stub I did, I think I did it as an example. It's not so much for this, but anyways, all of this so far so good, all right, in what we have. So we need a stub that is short circuited. We need to put it in series, and we need this short circuited stub to give us a positive, all right, not a negative, to give us the short circuited stub needs to be practically the 42 point. We need to, this is 42. It's the stub is not it's not the stub. The stub needs to be plus point, all right, 85. In any case, let's take for a positive, 85 is gonna make it even longer, because positive 85, that means that we are not down there as I put in the stub. I will stop it here because I need to correct the stub, this one. I mean, even this is an example, right? Let's use that as an example, but this is not your correct number. It's an example for the stub rather. But you can see that the stub here, use that as an example to see that the stub, if it's up for this particular case, for this point, if you want to be at this point, an open circuited stub is going to have a shorter length than a short circuited stub. At any other point, if you're up here, for example, where we are going to be eventually, if you are up there, then a short circuited stub, there, a short circuited stub is going to have a shorter length than the open circuited stub, which is going to start from here and go around until you come to this point. Why am I saying that? So what you need to remember, and we're going to cover it on Monday, that always the length is going to tell you what to choose, an open circuited or a short circuited stub. All right, whatever gives you the shortest length, because you don't want in your designs to have a stub which is too long, because if it's too long, it starts radiating. It creates parasites. All right, if it's not radiating and it's all buckets, it's going to create parasites. So you always go for the shortest practical length. And we are going to finish with this. So this is designing the stub, practically design. I will clear this up, so I will put notes so you can remember it on exactly how we are thinking of the design of a stub. All right, that for every stub, for every impedance of a stub that we want to create, there are two possibilities. Either create it with an open circuited or create it with a short circuited. You can do it with either one. But what you're going to select is going to depend on which one gives you the shortest length. So that is what we are going to learn from here. I'm going to rewrite this part up to here. We are all good. And then we are going to finish this up next time. And the other thing that I will do after we finish it up on Monday, we start another problem. So we'll do more problems like this anymore. Okay, that's what we're going to do all of next week. Now, next Friday, and I will send you a note, and the following Monday, I'll be traveling. So I'm gonna put the lectures on Zoom, and I will make the lectures available during and after that. I will start them. I will start the video at the time of the class. All right, and it's gonna stay open after that. So you can, for those of you who have who take the class in the morning, you can at 8 o'clock go through the video. I'm gonna solve problems, and then it's gonna be an hour, 50 minutes. The same thing on Monday. And on Tuesday, which is a redefined day, we are going to also solve problems in person here. And we are gonna do that, the problems after this, the problems that I will give you for transmission lines will be very similar to the problems you're gonna see in the final. And in the final, you're gonna have, we'll talk about that too, one problem with different questions from the second part of the course, one problem from the first part of the course. All right, so that's how it's gonna be. And we are gonna solve problems from the second part of the course primarily because we had the midterm and all of these many examples in the front part, but the second part, we need more problems. Any questions about this, any suggestions? If you have any suggestions about